Goedemiddag allemaal. Good afternoon, everybody. Welcome to our monthly Tech Talk. This is the third session of the year, and today's subject is mechanical seal support systems. My name is Leonard Monster. I'm a field engineer at Swagelock, and the presentation will be held in English today, and the presenter is Sean Hunsicker. Sean is a market manager, chemical and refining at Swagelock Corporate, with a special focus on seal support systems. And he will try to tell us more about that today. If you have any questions during presentation, you can ask them in the chat. We will try to cover these questions during the presentation or afterwards. And well, let's get started. I would like to give the floor to Sean.
Goedemiddag, everybody. Thank you. Good afternoon. That's about all I know in Dutch, so I'll leave it at that and continue in English from here on out. I'm coming to you from Cleveland, Ohio, where Swagelock corporate headquarters and most of our manufacturing is. So I've prepared a presentation today about seal support systems and my experience in working with two aspects of seal support systems. In my role as market manager for Swagelock, I work with the OEM companies that produce the pumps, compressors, and other pieces of rotating equipment, as well as on-site go to chemical plants and refineries around the world and work with our end users on applications around seal support systems. Okay, let me advance the slide here. Okay, so for today's topics, I'll give a little overview on API 682, which is our guiding document from the American Petroleum Institute on rotating equipment for seal support systems on pumps. I'll talk a little bit about piping or tubing, as we do have a choice what to use there, and then really cover some points around reliability and safety, designing these systems to make sure they're both reliable and safe. And then I'll finish up with a little information on some of our evaluation advisory services around seal support systems. Okay, so the current edition that we're dealing with for API 682 is the 4th edition. It came out in 2014, so we're looking for a current update to that coming out in the next year or so. I do want to mention right away up front that it really is a standard for the sharing of best practices around seal support system. It is not a code like ASME B31.3. So it really is a set of recommendations. Now, I know many companies adhere to API 682. Some companies, like I've dealt with Shell in the past, they'll have additional requirements that they put on top of API 682. But I think as I go through the presentation today, I hope you get to see that it is a recommendation, and there are times when it might be beneficial to you to deviate a little bit from what API 682 recommends. Some of you out there attending might be in a chemical plant where you have a mix of API and ANSI systems. We always start with API 682 as it is the design standard, the gold standard for us, and then work down from there. If it's an ANSI system, sometimes we can substitute components if it's an ANSI system. In API 682, I really focus from a tubing and piping perspective on two areas. Section 8, which calls out all our requirements for accessories, as well as Annex G in the back, gives us the standard piping plan diagram and all the auxiliary hardware. So those are my two big reference points in API 682. Throughout the standard, the real message that API tries to get across is to design these systems for reliability, safety of everybody in the area, and the operation of the pump itself, as well as ease of maintenance. So those are some things we'll talk about today. So they're called piping plans, right? API talks about piping plans. But really, as a user, as a designer of these systems, you have a choice whether you want to use piping or tubing. The term piping plan is just a legacy term that has been implemented since these plans first started being designed in pipe many, many years ago. I just pulled up here an article from Hydrocarbon Processing by Heinz Block. He is, worked for Exxon for many years and is, kind of the Yoda of rotating equipment, so to speak. And so he recommends using tubing. And quite frankly, over the last 15 years, many of the seal companies, many of the OEMs making pumps have implemented the use of tubing. So I'll talk a little bit about that choice next. These are the tables from API 682 that reference the size and wall thickness requirements for both pipe and tube. You can see here that the top chart talks about pipe sizes up to 4 inches. The recommendation for tubing usage in API seal support systems gives you guidance from 1/2 inch all the way up to 1 inch. So it's quite common that we see now across rotating equipment, even in the compressor world, using tubing up to 1 inch. I did want to call out here the difference in wall thickness recommendations for API applications. When I work with customers, sometimes they'll have instrument tubing, and I want to make clear that API recommends a heavier wall thickness than is required for the pressure and temperature of services in this instance. And they do that because they want that tubing to be externally robust. I mean, it's in an area around the pump typically, or a heavy piece of equipment. So it's really for rigidity and external robustness. The burst pressures on these heavier wall tubings are far, far in excess of anything you'll ever see in many of these pump applications. So it's really just for rigidity. But we do want to conform where possible to the standard. So I just wanted to make a mention of check that wall thickness and use the appropriate wall thickness tubing. So I thought I'd start with a little case study here on a big pipeline pump. This is a big 1 meter pump diameter pipeline that is pushing from Texas hydrocarbons up through the rest of the United States. What we're looking at here is a bearing lubrication and seal flush system. You can see all the white piping, threaded pipe around here. This customer in particular had a high service item, which was the bearing housing there indicated with that red arrow. And they did a calculation, a time study, and found that it took them about 40 hours to access the bearing housing by having to disassemble all that pipe work. So that 40 hours was a few guys working, for about a day to disassemble all that pipe work. They had problems with the pipework in general. All those threaded connections were potential leak points. That pipe was heavy. It tended to vibrate itself and create leaks by shaking next to the pump. So, when we look at, seal flush systems like this done in pipe, many customers are looking at implementing a tubing solution instead for a variety of reasons. And I think this next picture right here on the same pump will show you really some of the benefits you get from using tubing in these applications. First, now you can see the bearing housing on the right-hand side there sticking out to the side. Accessing that now is a lot simpler when they switch from tubing. They gained the advantage of going from a carbon steel system to a stainless steel system. They didn't have to paint it now, so that saved them time and money on the installation. You can see that we've routed the tubing quite close to the pump itself. It's well supported, so it vibrates with the pump in tandem. It does not shake itself to pieces over time. And the bent tubing allowed them to reduce potential leak points as well as improve flow characteristics. So in this particular application, they were able to downsize in some of the lines from 1 inch pipe to 3/4 inch tubing due to that improved flow characteristic. So there are places in even large pumps such as this one where there is a benefit in terms of using tubing. Another clear thing here too is you can see that the filter is a serviceable item, and it's easily identifiable. With the other piping system, is quite challenging to identify what were the serviceable components. So just keep that in mind as we kind of go through. Piping or tubing is a choice you get to make, and if you have any questions, certainly guys like Leonard or myself are happy to help you choose the appropriate tubing for that application. Okay, so I'll start talking a little bit about designing these systems for reliability. And one thing I wanted to mention right up front is that in the annex in the back of the API 682, it gives you an ISO diagram. You're seeing here what they call piping plan 12. Please note that below the ISO diagram, they will have a little section there where it describes the purpose and the function of the system. And you might see language in there where it says, this design has not been proven to have a 3-year successful operating life. Okay. Now, you know, your seal manufacturer may say, well, we use a Plan 12 on that. And if you say, well, it doesn't have a 3-year operating life, that's really just to notify you that there's an item in here that may require a maintenance procedure, that it won't last 3 years without some intervention on your part. And in this piping plan, that is due to that strainer. It could be a reliability concern by becoming clogged over time. So I'll show you how some customers have dealt with that situation. You know, we want to reduce the leak points in these systems, and clearly in the API standard, it says, let's get rid of threaded piping. And I'll say that, you know, probably I'd say about 80 to 90% of our customers who had threaded pipe installed in these locations over time have gotten rid of it, and they've gone either with piping or bent tubing to reduce those number of leak points. So when we're designing these systems, we want to make sure that we view every connection as a potential leak point and eliminate them as much as possible. You know, these are around pumps, and there's a lot of vibration, there's temperature changes. All of that works against threaded connections quite heavily, and we certainly don't want to cause leaks in or around pumps on flush systems. However, like I said, this hasn't demonstrated a 3-year successful operating life without, you know, blowing down or servicing that strainer. So sometimes we may need to deviate from what API is saying for a period of time to help diagnose the situation. So I'll show a picture here of some areas where we deviate from, you know, API or add additional instrumentation. So here's an installation of a Plan 52 and a Plan 11. And what I'm looking at right here is this use of an orifice plate in the system, right? Similar to a strainer that can become clogged, especially in, you know, certain applications where there could be solids in the line. You know, there's no way for the operator right here to know that orifice is becoming clogged. So it could be advisable, if you have problems with strainers clogging or orifices clogging, to add a gauge after or before around those items to determine how quickly something is clogging by taking a differential pressure measurement. That doesn't mean that we need to leave that, you know, static in those gauges in place at all times. But this might be a place, if I had this clogging quite frequently, I may add a gauge temporarily just to monitor that orifice. I also look at, you know, connections in and around the pump. We said, you know, eliminating connections is a big deal. These are what, 1, 2, I think that's 3 or 4 fittings in there, threaded together to make the final connection into the seal. You know, this is absolutely not recommended by API to use that many connections. Each one of those is a potential fail point. Up here in Ohio, we have quite nasty winters. We have a lot of freezing and thawing cycles. You know, that also causes an issue. So we try to eliminate this. Ideally, we want one connection going into the seal chamber there. And I'm sure you guys have seen on the picture right here, one of the worst things I'm looking at is the use of hoses in these applications. Those are definitely not recommended by API. You know, hoses are fail points. They will fail. You can see, you know, the kind of blown up picture on the right there shows that hose starting to sag and kink. I can't tell you when that hose will fail. I just know that it will fail at some point. So wherever possible, we would recommend, you know, hard tubing that up directly from that Plan 52, from that seal pot into the seal itself. So definitely don't use hoses in API circumstances. So in eliminating those leak points, you know, there are a variety of products out there. These are extended, longer fittings to help get you out past the shroud and make a good connection to tubing. It's just basically a regular swage lock fitting, just made longer. And that's just to avoid the use of 3 or 4 fittings to make that connection. You can see that picture in the middle there. You know, it's got a piece, a pipe nipple, and then a hex coupling, and then your tube fitting on top of that. Now, those are just 2 additional leak points that aren't necessary. So I encourage, you know, when we're designing these systems and installing these systems, that we give the installers the correct components to make those connections. Because if they're just drawing from their storeroom or whatever their toolbox on their cart is, it's quite likely that they'll just grab a bunch of fittings and put them together. And we really want to use and look at each of these systems and eliminate potential leak points as much as possible. Another area I see a lot of potential leak points around is when we have instrumentation, particularly thermometers. Here where you see tubing where they've adapted a piece of pipe to hold a thermometer. And one of the challenges with this is I'm looking particularly at the way that that thermal well is threaded into that pipe right there. Let's say we have somebody come on site to change out a failed thermometer and they put their wrench on the wrong hex there and they accidentally unthread that thermal well. Now I have an uncontrolled release of process fluid into, right on the installer. And so it's certainly a bad scenario. So make sure when we're looking at connections, not only as potential leak points, but as also, safety considerations where if somebody's maintaining something, is it possible for them to accidentally disassemble something and cause a loss of primary containment? So there are products out there, this is called the thermal well T, where we weld the thermal well into a tube fitting. You can see on the right there that we've installed two thermometers and through the thermal well T into supply and return lines for a seal pot. The reason we weld that thermal well into the fitting itself is so that somebody couldn't accidentally disassemble it. Now somebody can come into that system if they have a failed thermometer, unthread it and thread it back in without ever exposing themselves to a potential process leak. So not just Swagelok, but any of your vendors around this, I think it's a good idea to engage them and say, hey, let's look at these systems. How can we eliminate potential leak points here or potential safety concerns? API also recommends now that all instruments have block and bleed valves. I know that seems like a very simple point, but in my experience in the field, I cannot tell you how many times I've seen process gauges threaded directly into process piping. And that causes a problem because then when that gauge fails, there's no way to isolate that without taking the pump or the system offline. I mean, we have that gauge there for a reason. We want to read pressure. In this instance, you're seeing a flush line from a between bearing bump going to each of the seals right there. Just the simple addition of a block and bleed valve on each of those gauges makes it possible for you guys to change out that gauge if you have a failure. We're reading a pressure drop across an orifice in each of those fittings right there at the base of that gauge. So we want to know that pressure. If we didn't have the block and bleed there, we couldn't disassemble it. So the recommendation from API is definitely block and bleed on every instrument where possible so that we can isolate it and change it if needed without having to take the entire pump system offline. Additionally, one of the direction that we're going in the world of seal support systems is clearly favoring transmitters. So we want, a constant stream of information. We want to be able to monitor trends. That's the way it's going. However, there may be times when just a pressure switch is appropriate and you don't really need to trend that data. So even though it says, we want to go with transmitters instead of switches, on a Plan 76, you're monitoring gases coming from the seal, going to the flare, and you're really just trying to read if there was a failure event. So you just want to know if there's a pressure spike in that system. So maybe there a switch is okay. On the right there, you see some, on the 74, which is supplying clean, dry nitrogen into the seal. A transmitter, maybe in that instance, the transmitter is the better option. Because we're really wanting to monitor that flow and pressure in that system at all times. So the direction is definitely towards transmitters, but we still see a lot of switches out in the field, and really that's up to you where you want to use a switch versus a transmitter. So I think the future state will be more constant monitoring through transmitters of all these systems. Consider too, when you're designing these systems, again, that functionality or that ability to add and subtract instrumentation easily. There are features of items such as like a tube stub on the bottom of a gauge that allows it to be easily dropped in and out. If you look at the picture of the Plan 76 right there, we have the process gauge threaded into a block and bleed valve, but then bolted to the back of that panel. If that gauge was to fail, it might be difficult to remove it. So when we're designing systems, we always want to make sure, again, that other higher level concern, ease of maintenance, are the items, even gauges, easy for me to take off and replace. The picture on the right shows a well-designed panel where everything's front mounted, so that it could be slid off the panel, disassembled, and replaced without having to take the entire panel offline. So just a few considerations on designing for reliability. Okay, I want to bring up something too about vents and drains. The API, the standard says that all auxiliary systems shall incorporate these vents and drains as necessary. So what I've highlighted here is the tubing that goes from an API plan 53B into the pump itself. On this system, high point vents are fairly critical because you could get a slug of air trapped in either your chiller, your cooler, or that mechanical seal itself. All of those entrapped air cause issues. If we're not providing our installers with the proper components and design to show them where to put these high point vents or low point drains, the likelihood of them being installed is very, very small. If a 53B arrives on site and someone says, you got to go install that, they're just going to grab tubing and maybe some fittings and put something together. I've seen lines mixed up. So I really encourage us as owners of the equipment and being responsible for these systems being reliable. Think about how is that seal support system connected to the pump? Does it have the right components? Does it have the vents and drains? And a simple drawing like this and a kit of components really helps an installer install something like a 53B correctly so it operates correctly. I'll show you, a couple of slides here and pictures on some unsafe installations, but this is the reality of what I see on the field. API tells us that we really, really want to make sure that all of our seal support systems, any kind of instrumentation on that is at eye level, easily visible, and all the components are accessible for us to work on. What you're seeing here is actually probably the worst example I've ever seen of a Plan 32. If you know what a Plan 32, that is delivering an external flush into the seal chamber at a higher pressure than the seal chamber. So in this instance, it was a water flush system, but hastily constructed, ill-designed system. I'll show you, kind of walk you through it right now. We've got water that comes down from the top through a hose. Already mentioned, hoses are not a proper installation in this application. It's got to make a real hard U-turn up into my flow indicator, through a rusty strainer, hard 90 degrees through a rusty old check valve, and then you can see that green arrow pointing to a half-turned ball valve for flow control. So right away, this is not a great situation. If I've got somebody coming out on site to work on that pump, clearly they may say, gosh, should that ball valve be open? Should that ball valve be closed? Either instance, ball valves are just not meant for flow control. So not a safe installation there. Also, just look at the entire system here. My flow indicator is down on the ground. If I have somebody walking around the plant, checking systems and making sure flow is appropriate, every obstacle we put in their way, even make them bend down and look at something on the ground like that, the likelihood of them doing that regularly is not good. So we want to make sure everything's up and at eye level and easily readable. So even something like a Plan 32, whenever possible, I like to see panels around these systems. All seal support systems should have things at eye level or on a panel wherever possible. It just makes it cleaner, easier to work on, and it looks like a system. In that previous drawing, it's just components around the pump. When it's put on a panel like this, it looks like a complete system. Now I have a high quality flow meter. I've got my pressure there. I've got my temperature information. I could block and isolate my strainer. I can put gauges around it to see if it's clogging. And most importantly, I'm using the proper components. I have a needle valve to control my flow. So my, saying around designing seal support system is make sure the design is intuitive and the function apparent. When you have an operator walking up to a panel, they should be able to see that it's a system, and it should be easily identifiable what's going on in that system. Here's a picture of a Plan 74. Plan 74 in a dual seal arrangement delivers clean, dry nitrogen into the seal area there. And here's a good example of using a panel. And here we have somebody writing using marker on there, some directions to operators. 55 pounds on the gauge, the pressure of nitrogen, don't adjust. But if you can see the little writing next to the upper flow meter there, it says at 5, and there's using standard cubic feet an hour, we'll write the maintenance order. And at 10, they will change the seal. So I'm glad to see that they're putting some instructions and some guidance on there for their operator, but I think we can do a better job than just using a little black magic marker to hand write notes on there. So I'll show you a few examples of some really well-designed and detailed panels. This one right here is a combination panel for a 7276. Okay, so the 72 again is a clean, dry nitrogen, delivering that to the seal. The 76 is our leakage collection plan that's sending a mix of processed gas and nitrogen to flare. So you can see what we've done here by using a color coding system on the back of the panel, that the two systems are different colors. The 72 is in white, the 76 is in orange. The colors also denote a material difference. Because that 76 portion handled a mixture of processed gas on an ISO stripper in a refinery, it could have some acid in it, so it's designed out of Monel. So now an operator walking up to this can clearly see we have two different systems here, we have two different materials, and you can see that's noted on the panel as well. We also have instructions all over this panel. You have nitrogen set point at the gauge, as well as the regulator controlling that pressure, so that there's no confusion that we need 2 to 3 PSI to the seal. We've got other things like operator instructions that the gas to the seal should be first on and last off. We're noting where there's isolation or block valves. So I just encourage you to think about what kind of information can we put on the panel that helps operators or maintenance technicians understand what's happening on the panel and how the panel should be operated. The nice thing about using these kind of wraps or cards on panels is you really could print or put pictures of whatever you would like on there. And more often now we even see customers requesting QR codes on the panel that they can scan and bring up designs or other operating instructions. So it's just a consideration that I think we should all try to make these intuitively designed and that function apparent to all of our operators. Okay, one of the last points on, kind of the important points of API 682 I'll bring up is the filling from grade of seal pots. There is clear indication that it's no longer acceptable for people to climb up on top of the pot. So I took a picture here of some Plan 52s at a site where the refill procedure for these pots, when they needed to pour some fluid in the top of them, was not safe or efficient. It took them a long time to get around to all of these pots. They had to climb up on a ladder, possibly shut down the equipment to cool it off. They had health and safety issues whenever they took that pipe plug indicated with a green arrow off the top of the pot. You could be exposed to, some pressure in that pot, or there could be high temperatures in that area, some vapors from whatever gases were coming in through the seal pot itself. So this customer was clearly looking for a solution to really address how do we stop climbing up on the top of the pots to fill them up, and we wanted to fill them all from ground level. So in order to do that, we embarked on a transformational process with the customer to retrofit every seal pot across the entire facility with a fill assembly. And a fill assembly is just simply tubing that ties into the top of the pot and comes down into a valve array to allow you to fill the seal pot from ground level. And it really provided the customer with a couple of advantages. They did not have to take the pump offline anymore to fill the seal pot. No use of ladders. So it just really addressed a couple of issues for them. And most importantly now, the operator could work from ground level. And they, over time, were able to implement this on all the seal pots across the entire facility. And this facility had Eagle Bergman, John Crane, FlowServe seal pots, and we were just simply retrofitting each of those pots with the same fill assembly. So now they only had to train their operators on one method to fill seal pots. So little projects like that around standardization can play a big role in increasing reliability and safety. And there you can see on the side, that's part of our standard design. When we build seal pot systems now, we incorporate that fill arm, that safe fill assembly on everyone. And that can be designed, to always be 1 meter off the ground level for easy filling. Lastly, I'll talk a little bit about what we do when we get on site around seal support systems. The gentleman there on the right is wearing what we call a RealWear headset. He's got a camera in there. He's communicating with engineers back at the factory here, like somebody like myself or somebody like Leonard. Sitting behind the scenes can actually view what we're viewing through that headset, and we start walking through and identifying what's on the pump and how does it compare to two things. The first thing is API 682. How does the installation compare to what we know is a best practice, as well as then what's a best practice or most effective technology on your site? Is there requirements that you have? So we compare them against known standards, and we generate a report in an area or across a series of pumps. So I'll just give you some results on that. What we do is asset realization. Some of the things that in particularly older sites, that is a challenge is we found a lot of our older sites, they may not even know exactly what's out there. So this is part of our process, is just documenting what's existing in the field. Things get changed over time. So it's good to know, what do I have out there? And then we identify deficiencies or gaps in standardization, safety, reliability, and compare that again against API 682 or your own company specified most effective technology. So each system, each pump is identified, recorded, and reported. And I'll just highlight some of the reports. You're seeing on the left there our documentation tool that we've developed. So we're looking at the API standard design, and then we're cataloging deficiencies against your own standards and API 682, coupled with the pictures of what we find in the field. And then what we do is kind of give a little recommendation and categorize each issue that we see in the field. And so some of these issues are going to be minor and something that you can fix over time, and some of them are going to be quite high and important to fix almost immediately. So we try to categorize and organize the information from our findings in a variety of ways so that you can look at this data however you'd like. So some of this stuff would be statistical findings on types of plans per area. This site had 53 As, 40% of the pumps had 53 As on them. So some of this is just documenting what's out there. So that's what we're doing on site right now. And I just wanted to say, is there any questions from the group?
Well, thank you, Sean. I think it was a great presentation. We're a bit running out of time, but if anyone has any question, please reach out to us. We will be able to answer by phone or by email. Sean, thank you very much for this presentation. I would like to thank everybody for listening. Our next Tech Talk will be on the 22nd of April, and the subject will be tube fittings plus medium pressure products in hydrogen applications. This Tech Talk will be in Dutch, and well, hopefully we will see you all then. So have a great day, and thank you very much, and hopefully see you next month.